Christian, what's your question?
Oh my.
With problem number 5, like, how can the area be shrinking if it's a
Surface area.
surface area? Like, I mean, even though the object still has its
Because think about a balloon. It has properties of elasticity, right?
yes.
So its area
Oh,
can
so
change.
true.
Take a rubber band. A rubber band's surface area is the area around it. But the minute you go like this, I know it gets smaller, but the surface area does go up a lot. Take your shirt. Anybody have any shirts that are stretchy material? I'm not going to stretch it a lot. But if you took like your sleeve right here, there's the area. Now we do this. Didn't the area get bigger? It's just surface area. That's all it is. It can change. That's what the word you're looking for here, by the way, an elastic thing that can change is called a membrane. A membrane, like a cell membrane. Remember biology. If a cell is dried out, it shrivels up. If a cell gets a lot of water, it gets supersaturated, it gets diluted, it starts to expand the cell membrane. Right?
It's what?
Okay. The
Valuable?
malleable, yeah, malleable is something that can be changed. So you would say that like rubber is very malleable, or clay would be malleable, it's formable. Ductile is another word for that, but ductile has to do with the stretchiness of something. It was what? Shine would be when a metal is shiny, the word is not ductility or ductile, but
Hold up, he knows it. He just said it.
there's another word for it. It's not
It was a show.
metallic. There's a word for the shininess of metal. I forget.
Google it.
Shininess of metal?
I know the word, I just don't remember the word.
Shiny.
Shiny metal?
Okay.
Bender?
What?
Element. Alloy.
No, Alex.
You should have said, what is the word for
What is another word?
for shininess of metal?
Gold, platinum, nickel.
Yes,
Transition.
let's just throw out random elements because they definitely mean shiny.
That's not the right one.
It's not lustrous. Lustrous has to do with light. Maybe there isn't a word for it, and I'm just making it
No,
believe.
you didn't Google it correctly, Mr. Howell.
What do you want me to Google?
Let me do it.
Just tell me.
Oh, go to Google.
I'm in Google. You know what I'm in Google.
Alright, what is the word for the shininess of a metal?
It's called shininess.
Why'd you come up with these?
Wow.
See?
Nice. Luster, it looks like. I think it was luster.
Luster.
Yeah.
I thought that was for hair.
Yeah, that's just shine. I guess we
No.
Yes.
Alright,
Go to
number
Google.
6.
Google.
Google that symbol. That's how we.
What a waste of like the first thing they're gonna see too. It's like why did
You know what? You read this one last night. Let's go to a harder one that has a pyramid that's inverted instead. We did a cone already a few times. Let's jump to a pyramid.
But I think this never happened.
It's just like number 5.
I'm just gonna pull up a problem. Hold on.
Luster? What is
You don't have this packet yet, guys.
Chop the video.
Chop the video.
Cut that whole part.
Want to just start over from the beginning?
No, it's the imperfections that make
Because you
us
know
who
how
we
annoying
are.
when
Here we
you're
go.
going over the
Wow.
percentage
That's
of
right.
the exam physics to watch. I just wanted to skip it.
Why? We just talking about
And then
you.
press it. Yeah. And then you show the graph.
Said I don't remember anything.
Alright. Let's take a look at this problem now. I can give you the packet that this is in if you'd like right now. We're not going to do that anyway right now.
Yes, because I
You don't
need
have to
that
write it all out.
paper.
It's number 7 in this packet.
You get that.
Paper.
Thank you.
For education.
Right.
Okay. I kill people for the sake.
Okay,
For the safety of other people.
Hey,
Don't say
Their
your
end is
name.
justified.
turn to number 7, please.
Yeah, because they're gonna rough you up.
Can you label these 3, Jones? For Kenny, Edgar, and Jasmine?
What
I
number
was
we?
going to ask you, but I thought exactly that. Sorry.
It's okay.
I know that's me.
At least you got it. At least you get the problems right.
Alright, so I want to take a look at this problem here. It has a pyramid instead of a cone. And I'm going to have you guys work on another problem after this together. So a pyramid instead of a cone. Now, a pyramid, again, is 1/3 of a prism. Again,
I thought it
if you
was
had a prism,
1/3 of a square.
No.
if you had a prism like this, okay,
So it's not a
and
cube,
you
it's a
had a
prism.
pyramid. Imagine the pyramid came to the top right there. The same exact pyramid,
Cube is just a
same exact base.
equals high.
Imagine that pyramid. See that green pyramid in there? If it has the same base and it has the same height, it's 1/3 the volume of the other one. So if you wanted the volume of the prism, it's LWH. If you want the volume of the pyramid, I'll put PY there. We're going to say 1/3 LWH. Okay, where L is the base length, W is the base width, and H is the height of the actual prism. These are other ones that you need to have memorized, guys. Again, if you want, put them in your calculator, though.
I'm
Okay,
about
put
to
the
do
formulas
that.
in there.
No,
You have to know what they mean.
Big
If you just
deal.
write DP equals LWH, you gotta know what that means. Yes. Do you know how to write a program in your calculator, most of you?
No, yes, no, no.
Okay, after we do this problem, tell me, we'll make sure we take a look at that real quick.
No program.
And I mean write a program that's simply just text, not an actual program. You can write many programs. That's list and stuff, yeah. We'll go to doing that. All right, so water is poured to an inverted 10-meter tall pyramid shape. So now I want to look at this. It's inverted, and it's 10 meters tall.
What? Man, that's twerk.
Okay, I know it's tough to draw. That doesn't really look too good.
Doesn't
Okay,
matter.
oops. Actually, the dash line is off. Whatever. Okay, so you got a pyramid that's inverted, okay, and it's water being poured into it, 10 meters tall. So we know the height of the pyramid already is equal to 10. The square base of the pyramid has a side length of 6. It's a square base, so it's 6 by 6. We're told that water is poured in at a constant rate of 3 meters cubed per minute. So is it gaining volume or losing volume?
That's a
It's gaining. Very good, Carrie. It's gaining. How come? Poured in. Guys, the water is being poured in. Okay, so it's gaining volume.
I'm still over here. This is WE.
Okay, so we're starting with our rates now. How fast is the water level rising when the water is 2 meters deep? So we want to know the water level. So what am I taking the derivative of? What tells me the water level? The what?
The surface volume. No. Volume. Wait, say your question again.
The height.
If I'm outside in the backyard,
The height.
if I'm outside in the backyard and I want to fill up my pool, and I don't know what the water level is, you would
The
look at the
height.
height the water is, right?
Look at the volume of the.
So what you ask?
So water level is DHCT,
I look at pH.
and that's our question. Again, guys, you're always looking at DDT of some geometrical constraint here, or some geometrical portion to the figure. So the height here is what we're looking at. The only other option right now is really volume. You couldn't have done DH anything else, okay? And you could have done like DHDS or something for the sides there.
Yeah, I don't even have this thing drawn.
All right, so how fast is the water level rising when the water is 2 meters deep? So when H is equal to 2. So this was D for dreads right here.
Thought that was us.
This was R for related rates, and then you realized, oh, we have so much more time.
Mm-hmm.
So, for this kind of a problem, I want to go ahead and see and think to myself, how can I figure this out? If I start with my formula, I'm going to notice I'm going to have a lot of variables. That's going to be the issue. So let's go ahead and take a look.
Are we gonna have to like choose?
Let's see. We know that the volume of a pyramid is 1/3 LWH, but L and W are both the same, aren't they? Aren't L and W both 6? It's a square base. So why don't we call it V equals 1/3 S squared H. Again, L and W are both 6. It's a square base. So call that S squared now. Now take a look, people. If I take the derivative, I'm going to need a product rule, aren't I? Remember how messy that was the other day?
No.
Okay, so I don't want to do that now. So I need to find a relationship between S and H. So take a look at the initial conditions. We haven't used them yet. The initial conditions tell me that when this is 6, this is 10. Again, when this is 6, this is 10. And this is moving down at a constant rate. It's very good. It's like, imagine you have a square on the top, then you make a smaller square, then a smaller square, then a smaller square. Isn't that what this really is here? It's like a bunch of squares getting smaller and smaller. Just like a cone. A cone is a circle, then a smaller circle, then a smaller circle, then a smaller circle, until you get to that point. So all of these squares are all proportional to each other.
So what does
They're all
6
proportional to the
represent?
height. So we know that when the
L.
S is 6, the height is 10,
Oh,
right?
the S.
What's that?
When S is 6, the height is 10.
Q.
So I can say now that when we could say S is equal to
3.
something times H. What fraction would that be?
3
Where are you getting that from? You're right. Where are you getting it from?
Oh, he got 6.
The proportion of
6 tenths.
yeah,
6 over 10.
6 over 10. That's all I wanted to hear. Very good. He's just reducing. So just without reducing, we would put 6/10 here. Because we clearly see that if we plug in 10 for H, we would get the 10 here, and these 10s would cancel, we get S equals 6.
So it doesn't.
Okay.
So it doesn't.
So we can put 6/10 or 3/5,
Oh.
but again, I'm just showing you where that's coming from.
Mhm.
So the relationship between S and H is S equals 3/5 H after reducing. Again, the side length is 3/5 of the height. Remember guys, remember optimization where we solved for W in terms of L and plugged it in to get rid of one of our variables? We're doing the same thing. We're going to plug this in now so that we have all H's, so that when we take the derivative implicitly, we don't have a product rule
Then we have
anymore.
the square.
We're going to have to square it, yeah. Let's go ahead and do that. Okay? Now, continuing.
Can't you, the B, 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 I mean, under B, like this.
We can take the derivative, but I want to simplify first, if that's all right. I'd rather simplify before I take a derivative. 3 and the 9 reduce. I'm going to get 3 over 25 H cubed.
Look at the.
What do you mean?
Yeah.
Oh, you squared it.
Square.
Squared.
Remember guys, when you square a product, you must square the top, the bottom, and the actual variable. And that becomes H squared. H squared times H is H cubed. Okay, if you want to write it separately as H squared here and H out here, that's fine. And then go ahead and combine them afterward. Either way though, this is now my volume. Does everybody see why we just did this? Why it's important?
Hold on, hold
Explain
on,
to
hold
everybody
on.
why it's important that what we just did to take the derivative. How come we didn't take the derivative up at the blue line up here?
B. Oh.
Because we're looking for H, so. when
We're
we-
looking for DHT.
Well, yeah, so we have two variables there, and here we can plug in everything except for H, so we can solve for it.
Exactly. Again, take a look, guys. We're looking for DHTT. If we took the derivative up here, we'd have a DSDT and we'd have a DHTT. I don't want to have to deal with DSDT because we don't have any information about it. So by replacing S with what S is equal to in terms of H, 3/5 H, we're able to ignore that. We're able to get rid of one of our variables before we take the derivative implicitly. Now take the derivative, please. Okay, we did DRE. This is equation. Now take the derivative of this.
H squared DHT.
Thank you. See, I almost forgot that, and I didn't need room.
You square. Going to.
Now, again, how do we do this? It's a power rule. That's all it is. Take the 3, bring it down in front. That becomes a 9. Replace the 3 with a 2. You get 9/25. You know everything in here now. What's the height that we were looking at the end of the problem it said?
2.
No, not 10. What is it?
2.
2.
Oh.
The height initially is 10. It says find DHDT when H equals 2, when the height of the water level is 2. So simply plug in a 2 here. What is the dVdt equal to? 3. And again, this was meters cubed per minute. And this would be the height, meters per minute. And we're going to square that, so it's going to become meters squared. Solve for DHDT. Again, people, think about these as variables. 3 equals 9/25 times 2 squared times x. Solve for x. That's what you're doing now. Think of this quantity as a variable x. If it was a variable, you would just solve like algebra. You know this value is 3, you place it in there. You know h is 2, you place it in there. Solve for x, or solve for the missing piece. What are you going to get? 25 up,
It depends on it's
75.
36 divided by 25.
I got 75 over, you're going to get 9 times 4 is 36. We could probably reduce it by a factor of 3.
Just put
25 over 12.
2.0.
25 over 12. What is it, Karen, the number? This becomes 25 over 12. And again, it's DHDT, which is meters per minute. Please remember, DHDT, the change in the height, meters, over the change in time, minutes. That's how you figure out your units again.
Wow. Do we have to simplify?
No, you actually do not. If you left your answer as 75/36 meters per minute with units, it would be correct. You never have to simplify. That sounds crazy, but that's the way it is. All right, I want you guys to try this one with a partner now, please. Go to your packet from last night and try number 14. The answer is there. The answer is in your packet, but please don't look at it. Try number 14. Okay, it's going to be a tough one, but clearly, please go through every step. D-R-E-D-S. Go through each one. Karen, I want you to work with Yvette. Rosie going to work with Kimberly. Terry, work with Cobb. Houston. Three of you, how are you guys going to... Actually, Houston, work with Rosie and Kimberly, the three of you together, please. Christian and Jocelyn, you got that?
What number
Terry
did you
and
say?
Cobb, Karen and Yvette.
I mean,
Are we good?
That's a blow.
Can you work with them?
What
Number 14. Number 14, please. Number 14. If you really get stuck, ask me and Mr. Carter, please. Go through your 4 steps.
Smooth. Let's go. I'm coming.
Guys, a right circular cone is just a cone. 1/3 pi r squared h. Again, a right circular cone, it just means that the height is perpendicular to the radius. That's all it means by right. Okay, that's a right circular cone on your left side there. So just a cone. Again, please make sure you both work together and it's not just one person. I'm going to pause the recording for those that are watching so you don't sit there forever. Okay, so for this problem, we're going to start by identifying what the volume is. Karen, you're working on what number?
17.
17. And I'm just recording something.
Wait, it says area.
Yes, number 17 is area again, guys. 19 is back to volume. I want you to try area first. That's 17. So a block of ice is in the shape of a right circular cone. So we know its volume equals 1/3 pi r squared h. We know that it's melting in such a way so that its height and radius are decreasing at a rate of -1 centimeters per hour. Again, only because it's decreasing. How fast is the volume decreasing? So the question again is to figure out what is dV dt. That's what we're trying to find right now. So we've got our diagram to start. We've got our related rates listed over here. We've got our other related rate listed over here. We've got our equation listed right here for volume. Once we know that, we can say, okay, let's take the derivative, but we'll notice right away that we are given both dH dt and dr dt. So with that said, if we take the derivative of v, we can use our product rule, and we'll notice that we'll have a dH dt and we'll have a dr dt. We'll be able to plug those both in. So if we think of r squared as a, think of h as b, and we take the derivative using a product rule, we have a times the derivative of b plus b times the derivative of a. The derivative of a is both of these two here. Again, the derivative of r squared is 2r dr dt. Once we plug in dH dt and dr dt, we'll see that we can plug in the -1 in both of those spots. That's right here and right here. We're also told that the height and the radius are both 10 at the end. If we plug in the height here and the radius here and here, we'll see that this number, this entire value, comes out to be -300. When that's -300, -300 times this 1/3 gives us the -100. The pi carries down, and we're looking at volume. Volume is centimeters cubed. Time is given in hours, so our answer is centimeters cubed per hour. Now we're going to take a look at number 17. Okay, number 17 is an area problem. That's the next one we're going to look at. So here,
Radius is
we're going to have the next problem to look at. We'll take a minute, do it together as in pairs, and then come back. Say it, sorry. So what I want you to do this weekend is take a look at this packet that I just handed out today, the related rates worksheet, and please look at numbers. We did what number today, guys?
7.
7, okay. Look at numbers 8 and
5.
you don't have, that's it, you all have is 8?
Yeah.
Oh, where'd 9 and 10 go? Okay, 8, see 7, we did,
I say we do 5.
Why?
Because it looks better.
you could do 5, it's like the one the other day, that would be a tough one. Here, do 8 and do 5. 8 will be pretty easy. 5 will be harder because you're talking about like a ladder. Go back to your example we did in class with a ladder and try and do 5 also. Okay, I'll post this link to this document on Facebook and by tonight.
Yeah, that's
Okay? Look in your pack of your other one for the ladder.
Thank you, Jim.